Welcome back to G Fun Facts Online. Today we are doing a deep dive into the hardware revolution that is quietly happening behind the scenes of the AI explosion. We are talking about the shift from the silicon age to what industry insiders are calling the glass age of computing. You have heard of Moore's Law, the observation that the number of transistors on a chip doubles every 2 years. For 5 decades, that has been the heartbeat of modern civilization. It gave us smartphones, the cloud, and generative AI. But that heartbeat is beginning to skip. We are hitting a wall. But here is the secret. It is not a wall of logic or physics regarding the silicon itself. It is a wall of packaging. The industry has a massive goal to fit 1 trillion transistors into a single package by the year 2030. To do that, we can't just make chips smaller anymore. We have to stitch them together in massive, complex 3D structures. And the plastic foundation we have been using for 20 years just isn't strong enough, flat enough, or fast enough to handle it. We are leaving the era of organic plastic substrates and entering the era of glass core substrates. Let's break down exactly why this is happening, the physics behind it, and who is winning the race to build the trillion-transistor future. To understand why glass is such a big deal, we first need to look at the weak link in your current computer. It is the organic substrate. In a typical chip package, you have the silicon die, which is the brain, sitting on top of a substrate, which is the body, and that connects to the motherboard. For the last 2 decades, that body has been made of organic materials, essentially layers of fiberglass and epoxy resin. Think of it as high-tech plastic. This has worked fine for general computing, but in the era of massive AI, plastic has 3 fatal flaws. First, there is the warpage problem. Plastic is soft. When you heat it up during manufacturing to over 240 degrees Celsius, it bends. It warps like a potato chip. As chips get larger and the connection points get smaller, that warping breaks connections, which puts a hard limit on how big we can make a processor. Second, plastic is rough. On a microscopic level, organic substrates look like rocky terrain. This roughness limits how fine we can print the copper wires or interconnects that carry data. We are hitting a limit at about 20 micron line widths. To get to 1 trillion transistors, we need wires that are 5 microns or smaller. Third, there is signal loss. Organic materials act like a sponge for high-frequency signals. They absorb valuable data energy and turn it into heat. As we move to massive AI data speeds and 6G networks, plastic becomes a bottleneck that slows everything down. This is where glass enters the picture. In semiconductor packaging, glass is a material superweapon. Its primary advantage is extreme flatness. This is a dream for lithography. While an organic substrate warps, a glass panel remains as flat as a calm lake. This flatness allows for a higher depth of focus in the machines that print circuits. The result is that we can print circuit lines that are 50% thinner than current limits. This allows for 10 times higher interconnect density. That means 10 times as many wires connecting chiplets, enabling massive data throughput. Then you have the coefficient of thermal expansion, or CTE. This measures how much a material grows when it gets hot. Silicon has a very low CTE. Organic substrates have a high CTE. When you bond them together and heat them up, that mismatch causes stress and breakage. But glass is magical because its CTE can be chemically tuned. Manufacturers can alter the glass chemistry to match the expansion rate of silicon almost perfectly. This eliminates stress and allows for gigantic packages that hold dozens of chiplets without cracking. On top of that, glass is incredibly stiff. It has a Young's modulus, or stiffness, nearly 3 to 4 times higher than organic materials. This rigidity allows the substrate to be made incredibly thin without becoming floppy, which enables thinner laptops and denser servers. Now, you might be wondering, if glass is so brittle, How do you drill millions of microscopic holes in it without shattering it? This is where the manufacturing technology gets really interesting. It relies on a process called through-glass vias, or TGV. Unlike organic substrates, which are mechanically drilled, glass substrates use a process that feels like science fiction, specifically something called laser-induced deep etching, or LIDE. This process was pioneered by companies like LPKF. First, an ultra-short pulse laser is fired at the glass, but it doesn't burn a hole. Instead, it changes the molecular structure of the glass in a tiny column, making that specific spot more soluble. Then, the glass panel is dipped into an acid etching bath. The chemical eats away the laser-modified glass 50 times faster than the rest of the panel. The result is perfectly smooth, tapered holes created instantly across the entire panel, thousands per second, with 0 microcracks. These vias are then plated with copper to create vertical electrical elevators that connect the chips on top to the board below. This technology is the roadmap to the Trillion-Transistor package. Intel has been the most vocal champion here. We can no longer make single silicon chips large enough to hold 1 trillion transistors because the defects would be too high. Instead, we are breaking the processor into dozens of smaller tiles called chiplets and stitching them together. Glass is the stitch. Because it is so stable and flat, we can place 20, 30, or even 50 chiplets side by side on a single piece of glass. The wiring is so dense that they act like one giant superchip. Furthermore, glass opens the door to optical I/O. Future chips will consume too much power moving data through copper wires. The industry wants to move to using light. Since glass is transparent, it is the natural medium for embedding optical waveguides. Imagine a chip where data travels through the substrate as beams of light, achieving unimaginable speeds with a fraction of the heat. Only glass makes this feasible. So who is winning this race? It is a global battle involving giants from the US, South Korea, and Japan. Intel is the pioneer. They have invested over a decade and $1 billion into glass R&D in Arizona. They plan to introduce glass substrates into high-end AI and server products in the 2026 to 2030 timeframe. Then there is Absolics, a subsidiary of South Korea's SK Group. They are building the world's first mass production factory for glass substrates in Covington, Georgia. Backed by the US CHIPS Act, Absolics aims to be the TSMC of glass substrates, offering the tech to any chip maker who needs it, targeting mass production as early as 2025. Samsung is also in the mix, aggressively building a pilot line to beat Intel's volume production, aiming for 2026 to compete with NVIDIA. And supporting them are the supply chain heroes, like Corning and Schott, providing the specialized glass, and companies like Applied Materials, solving the difficult task of coating glass with copper. However, we aren't quite there yet. There are significant challenges. The most obvious is the hammer problem. Glass breaks. In a factory designed to handle flexible plastic strips, a single shattered glass panel can destroy millions of dollars of equipment. Factories need to be completely retooled with gentle robotics. Then there is the issue of thermal conductivity. Glass is a thermal insulator. Silicon conducts heat 100 times better than glass. If a high-power AI chip sits on glass, it risks cooking itself. Engineers are solving this by drilling thermal vias, solid copper pillars specifically to carry heat away, but this adds cost. And speaking of cost, manufacturing a glass substrate currently costs 3 to 5 times more than an organic one. For now, this tech will be reserved for ultra-premium AI chips. Looking ahead to 2030, the landscape of computing will look radically different. Almost all high-end AI accelerators will likely sit on glass because the power and density requirements simply cannot be met by plastic. High core count server CPUs will utilize glass to support massive chiplet complexes. Eventually, as costs drop, the benefits of thinness and 6G signal integrity will bring glass to flagship smartphones. Glass core substrates are not just an incremental upgrade, they are a platform shift. Just as the industry moved from ceramic to organic packages in the 90s, we are now moving to glass. It is the invisible scaffold that will hold the next era of human intelligence.